Let's now move on to the Gram-Schmidt process. This is an algorithm by which you take any matrix. We will start with a square invertible matrix and we will try to get orthonormal columns in that matrix. So by definition, it becomes an orthogonal matrix. The Gram-Schmidt process is an algorithm by which you orthonormalize the columns of a matrix, thereby making an orthogonal matrix. Let's take a look at it. First of all, the algorithm works by projecting columns of the matrix onto the orthonormal versions of the columns that you've already created successively, and then subtracting away the parallel part. We will see how that works. But first of all, we have to look at the projection of vectors once more. So let's say you have two vectors, the red A1 and the blue A2, with an angle of theta between them. These are in Rn. So dot product is defined in two ways. One is by saying that is A transpose B, or in this case A1 transpose A2, but it's also equal to the norm of A1 times the norm of A2 times the cosine of the angle between them, cos theta. So you can compute cosine of the angle between these two vectors, cos theta, to be the dot product A1 transpose A2 divided by their norms, norm of A1 and norm of A2. Now, let's say you want the length of the projection of A2 onto A1. And by looking at the construction of the hypotenuse, which happens to be my blue vector, and the angle theta, then you can see that x is actually the adjacent side of a right angle triangle. So it's a cosine of the angle times the hypotenuse. The length of the hypotenuse, of course, is the norm of A2. So norm of A2 times cosine of the angle will give me the length x. And since we know what cosine of theta is, we can just substitute that to get this neat little expression there. Now, suppose you want not merely the length x, but a vector of norm x lying along A1, which is what we will call A2 parallel, because it's a part of A2 that is parallel to A1. That is that if you want to get that vector, then you have to take the norm of that vector, that light blue vector. The norm is by construction x, and multiply it by the unit vector along A1, which would be A1 divided by the norm of A1. So A2 parallel would be x times the unit vector along A1, which is A1 divided by the norm of A1. And then you can just put the value for x coming from here, that is A1 transpose A2 divided by the norm of A1. And after some rearranging, knowing that vector multiplications respect associativity, you can do this part first and then multiply by A2. And then you can recognize the norm of A1 times norm of A1, that is norm of A1 square, which you know is A1 transpose A1, the dot product of A1 with itself. So you get this expression. Let's look at it once more. What it is saying is that it's A1 times A1 transpose divided by A1 transpose A1. This is just a scalar. This is a number. What's on top? That is actually a matrix. And the whole thing multiplies A2 to give you A2 parallel, which is the part of A2 that lies on top of A1 as a vector. Now you can just look at A1 parallel, which is the part of A1 that lies on top of A2, by just swapping A1 and A2 in this expression. You get A1 parallel equal to A2 transpose divided by A2 transpose A2 times A1. That looks like a horrible expression, but there is a method to this madness that you will see soon. So this is the parallel part, but we are interested in the perpendicular part because after all we are trying to find orthogonal part of A2 with respect to A1, and then with respect to A1 and A2 you would want to find the orthogonal part of A3. Remember, A1, A2, A3, they are all columns of the matrix A. So we found the part of A2 that is parallel to A1 as a vector, then you can take one more look at it and you can see that this is actually A1 divided by the mod of A1, which is the unit vector along A1, which is what we will call Q1. And then you have A2 and A1 being dot producted. You know that A1 transpose A2 is the same as A2 transpose A1 because dot product is actually commutative. So you can take A2 transpose, then you see that there is A1 divided by the mod of A1 again. So that becomes Q1 again. Now, if you look at this expression, there is Q1, which is normal, that is a vector part that just says that A2 parallel is in the direction of A1 because Q1 basically defines the direction. And then what is the next thing that you have? You have Q1 transpose A2, this guy. What is that? That's a dot product of A2 with Q1. That is just a number. So it's a scalar. You can move it around anywhere you want. And also you know that that's the same as A2 transpose Q1. So you can write it that way if you want. All those things scaling the unit vector along A1. So you get a vector along A1 with some length, some norm, which is basically the dot product of the vector that you're trying to project, A2, and the unit vector along the direction of A1, which is what we call Q1. So let me say that again. The parallel part of A2, which is the part of A2 that lies along the direction A1, is the unit vector along A1 scaled by the dot product of the vector that you're trying to project, A2, and the unit vector along the direction A1, which is Q1. Now we got the parallel part, but what we are interested in is actually the perpendicular part. How do you get that? You have this little right angle triangle there. You have A2 parallel right here, and you're saying that A2 is a sum of A2 parallel and something else, which would be the perpendicular part. So you just subtract away A2 parallel, then you will get the perpendicular part. So just take it to the tip and subtract it away. Then you get A2 perpendicular. And that's the one that you want. So this is the basis of Gram-Schmidt. We are actually laying the foundations of the Gram-Schmidt process. But before we orthogonalize a matrix, maybe we want to know what it is and why it is that we are doing it. Given a square invertible matrix, we might want to get the orthonormal version of it, which means all columns are of unit length, that is the normal part, and they are orthogonal to each other, that is the ortho part, so orthonormal. So the columns of the matrix that you will get are orthonormal. You can use it as a good basis for the space that is spanned by the columns of the original matrix. So Gram-Schmidt process, and eventually, as you will see in about 5 or 10 minutes, it will lead to what we call the QR decomposition, Q being the matrix containing the orthonormal vectors, the orthogonal matrix, and R somehow encoding the sequence of operations, keeping tab of what it is that we did to get Q from A. It is used in several algorithms. We will go through just one later today, but by the end of this course, you will see that there are several algorithms that use QR decomposition as the first part. Earlier sometime we said that if you have an orthogonal matrix, it doesn't change the norm of the vector that it is multiplying. Why is that important? If you take any odd matrix and multiply a vector, you might get something that is very small, and if you multiply a few times, you might get underflow error kind of problem in computer science. The components might become too small, and then the errors, the precision of the processes that you're using might dominate the actual value, or it might actually increase the length and then there will be an overflow error depending on how many times you need to multiply. But if you know that the matrix is orthogonal, then you know that there is no underflow or overflow errors, and that is a reason why you might want to use Q instead of A if you can capture the operations that you want A to be performing on X in its orthogonal version Q. What Q really is that it preserves the direction of the first vector and it preserves the order in which the rest of the vectors appear, at the same time making sure that they are all orthogonal to each other. How do we do this? That is the Gram-Schmidt process. You take the first column of the matrix, normalize it, so that's just a scaling operation, and get the part of the second column that is perpendicular to the first one, normalize it, then get the part of the third column that is perpendicular to both the first and second columns that you've just created, and then you normalize it, and then you keep going until you run out of columns to normalize. So that's what you do. So I have one animation here. Let's go through this, and then we will go through a visualization, which might be a bit easier to see. So I have an n by n matrix. A is got n columns. Each column's got n components. So let's just consider the first three colored in red, blue, and green. So first thing that you do is take A1 and just normalize it, just a normal vector along A1. Then you project A2 onto it, get A2 parallel, subtract that away to get A2 perpendicular as a vector. Then you normalize it. Then you get Q2. So you have bright red Q1 and bright blue Q2. Then you project A3 onto both of them. You know how to project it to Q1, which is right here, dot product of A3 with Q1. That would be the magnitude, and then take the unit vector and scale that unit vector by this magnitude. Then you get the part of the third vector that is parallel to Q1 because it lies on Q1. Similarly, part of third vector parallel to Q2, exactly the same idea. Then you subtract those things away, both those things away, to get the part of A3 that is perpendicular to both Q1 and Q2. So you subtract away the parallel part onto Q1 and the parallel part onto Q2, and then you get the perpendicular part, and then you normalize it. And that's how you do this. And this is the process. If this animation wasn't clear, let's go through the visualization. I have the three vectors here, A1, A2, A3, red, blue, and green. The first step is to normalize A1 and call it Q1. So just take A1, divide by the norm of A1 to get a unit vector. The second step is to project A2 onto Q1. So you get the parallel part, then subtract that away to get the perpendicular part, and normalize it to get Q2. So you got Q2 here. Now you have Q1 and Q2, two vectors already. Right. Then project A3 onto Q1 and Q2. So you project it onto Q1 as well as Q2. So you get two different things there. The part on Q1 is pretty small because it just so happens that A3 was already almost perpendicular to Q1, as you can see. Then subtract it away to get the part of A3 that is orthogonal to both Q1 and Q2, and normalize it. So you get that. Now you can see the triplet of vectors that are all of the same unit length, and they're all orthogonal to each other. And that's how you proceed. So you can play with this to see how this actually works. Maybe some other angle might give you a better insight. It's up to you. Play with it. Now, let me tell you that what we're going to get out of A, first of all, you got Q because you know how to get Q1, Q2, and Q3. Q4 is the same idea, it's iterating forward, and you will get n vectors, each of which has n components. So essentially, you get an n by n matrix if you put all those Q vectors in a matrix, and that matrix is orthogonal and it's related to A. So you already got Q, and how do you get R? We know that Gram-Schmidt process is a series of column operations, so there are multiplications on the right of A. So let's call that multiplier, a matrix multiplying A on the right, let's call it X. So A becomes Q through the Gram-Schmidt process. The matrix that implements those column operations would be multiplying A on the right, just like the elementary row operations were implemented by a matrix multiplying A on the left, because those were row operations, column operations here, so on the right. So then you get an equation there. And by the sequence of operations, can you see that X has to be an upper triangular matrix? In order to get the first column of Q, we just took the first column of A, divided it by its norm, which means there's only one number in the first column of X, meaning Q1 was a linear combination of the columns of A. What kind of linear combination? scaling the first column of A by some number and scaling the second column by 0, third column by 0, etc., etc. So there's only just one x11 in X. The second column of a Q had some part of a Q1 being subtracted from A2 and then some kind of normalization going on. So that involved A1 and A2. So the second column of X will have X12 and X22. That is the part of the Q matrix above the main diagonal. And the third column will have X13, X23 and X33 as the elements. Everything else will be 0 because the third column of Q did not depend on the later columns of A. So it basically comes out of the sequence in which we perform the column operations. And so X, because of the process, is an upper triangular matrix. So to say that again, the first column Q1 of Q was a scaled version of the first column A1 of A, so just a scaling factor. The second column was a linear combination of the first two columns, A1 and A2, so just two elements there in the second one. So that's the reason why X is an upper triangular matrix. Now let's look at the inverse of an upper triangular matrix, and that is an upper triangular matrix also, which you can prove, and I believe that is an exercise for you in the in-class exercise somewhere. Let's call that matrix the inverse of X. Let's call it R. Now let's take our equation here, which encodes the Gram-Schmidt process, multiply on the right by X inverse, which is R. So A becomes Q X inverse, that is QR. So that is the decomposition. Now you might think that it's a pain to compute this X or this R, but it's actually very easy. Let me tell you why. Because if you look at A equal to QR, which is an equation, what is R? R is going to be multiply that on the right by Q inverse A. So R is going to be Q inverse A. Well, what is Q inverse? Q is an orthogonal matrix, so Q inverse is just Q transpose. Very easy to compute. And then just a matrix multiplication. So you don't really have to keep track of the operations to get R, but the programs that you use might actually do that. But you can do that by a transposition and a multiplication anyway. So R is upper triangular, being the inverse of an upper triangular matrix. You can see that not merely by arguing that inverse of an upper triangular matrix is an upper triangular matrix, which is true. Also, you can see from the fact that A equal to QR, how do you get A out of Q? You know that in order to get the first column of A, you just have to scale up the first column of Q by the norm of A1. So it's just a multiplication. That becomes the first element of R. In order to get the second column, you have to mess with the first two columns of Q, Q1 and Q2. So again, by the same argument that said X was an upper triangular matrix, R also is an upper triangular matrix. Now, there is a question that might be lingering in your mind. Why are we doing this? What's this idea behind QR decomposition? Why this obsession of decomposing a matrix anyway? Let me give you one example where QR decomposition is actually very useful. It is that we can actually use it to solve our AX equal to B instead of doing Gaussian elimination, which might have some numerical stability issues. We can use the QR decomposition. We know that A is equal to QR after having done the decomposition. Then AX equal to B becomes QRX equal to B because A is just QR. Now you can multiply both sides by Q inverse, both sides of this part by Q inverse to get Q inverse Q, Rx is Q inverse B, and Q inverse Q is just I. Then that reads Rx on this side is Q inverse, which is Q transpose because it's orthogonal, an easy thing to do on a computer, times B. So you can get Rx like that. And what's R? R is an upper triangular matrix. You know that if you have an upper triangular matrix, you can do back substitution very easily because the last row would just read some multiple of the last variable corresponding to the last column is some number on the right hand side, which is given by Q transpose B. After that, just back substitution is very easy. In other words, R has a perfect shape to let you do back substitution. Now, some of you might be wondering, multiplying both sides by Q transpose, is that a good idea? How do you know that the solution X here in this equation is the same as the solution to our original equation Ax equal to B? How do you know that? Well, one way to see that is that what we are doing here is multiplying both sides by Q transpose, because Q inverse is Q transpose. All we did was to take this Ax equal to B, put Q transpose here and Q transpose here, and we just realized that Q transpose A was just R, which we already had. So multiplying both sides by Q transpose. And my claim is that that doesn't change the solution. Why? Because multiplying on the left is basically taking linear combinations of the matrix on the right. So Q transpose A is just a linear combination of the rows of A, and the same operation being applied on the constant side. What are the row operations on a system of linear equations? They are equation manipulations, which don't change the solution set. That is the beauty of equation manipulations. So Rx is equal to Q transpose B will have the same solution set as Ax equal to B. Then you might wonder, we did perform column operations on A to get Q. We know that if you perform row operations, then the solution set doesn't change. Is there something that doesn't change if you perform column operations? Well, column operations are basically taking linear combinations of the columns. Then you know that the span of the columns of A will not change. We haven't paid too much attention to that yet, but soon, in a couple of chapters, we will. And that span is called the column space. And that doesn't change between A and Q, which is a property that we will make use of in linear regression. Now, we talked about square full rank matrices and what happens to them when we perform the Gram-Schmidt process on them. Let's also look at a typical data matrix, which would be called full column rank matrix. A in R m by n, m is greater than n, more rows than columns. Let's orthonormalize the columns of A, call them Q1, Q2, Q3, etc. How many of them will there be? There will be n of them, because n columns are linearly independent. They will become orthonormal. Let's put them in Q1. Q1 will have the same shape as A, and Q1 transpose Q1 will be identity matrix by the same argument that said that Q transpose Q would be an identity matrix. But on the other hand, Q1 times Q1 transpose will not be identity matrix, because that's a much bigger matrix. M, remember, is greater than n. That's not going to be anywhere near identity matrix. Ignore that for now. Much like the Gram matrix A transpose A was important, you can see that Q1 transpose Q1 becomes the identity matrix. And this, you can call that a thin QR decomposition of A when A is a tall, skinny matrix. A equal to Q1 R1. But R1 is going to be in Rn by n. And that comes out of the number of column operations that you need to perform. Think about it. That I will leave to you as an exercise to figure out why that is n by n. If you have a rank deficient matrix, we can get only R linearly independent vectors which can become orthonormal. A linearly dependent vector cannot become orthonormal to the set of vectors that it is linearly dependent on, because it is going to be on the same plane as the rest of the vectors or same subspaces. And you cannot find a perpendicular part, because perpendicular part will be 0. But the linearly independent ones will become orthonormal. So there will be R vectors that become orthonormal. In the case of a tall matrix, if one column or a few columns are linearly dependent, those columns will become 0 columns really, and the rest will become orthonormal. Can you see the similarity between that and our Gaussian elimination, where the rows that were linearly dependent became 0 rows? That's not an accident. It's just a transpose version of Gaussian elimination in some sense, except that we are doing a little bit more by orthonormalizing it. For a wide matrix, you know that the best you can hope to get would be all rows being linearly independent. So the rank is m, the number of rows. So n is a wide matrix, so n is more than m. So n minus m columns will become 0 columns. R columns are being the same as M in this case are linearly independent, and they will become orthonormal columns. So that kind of wraps up the similarity between Gram-Schmidt process and Gaussian elimination. They are related in that one is row operations, the other one is column operations, and one is like the transpose of the other, except that the purpose is slightly different, but the mechanics is roughly the same. So that brings us to the end of this video. My next video would be on things like the column space that we alluded to, the span of the columns of A, and then correspondingly we will have row space and some other spaces, 4 of them in fact. That is what we will see in the next video. But it is possible that I might create one video that might stand in between the next one, the next real substantive chapter, which is chapter 9, and this is chapter 7. So for chapter 8, I may create a video, but that would be like a synthesis of everything that we've done so far, looking at those things from a slightly different perspective so that you can review those things, but not as a repetition of what was already said, but as a different viewpoint. So stay tuned for chapter 8 videos or chapter 9 videos.